Hello, I'm Edward Tarte, math teacher. This is another in a series of solution videos to some of my math challenges. The math challenge for this solution video is my Pythagorean Toothpicks challenge. And here is how I presented that challenge in the original video. This is a Pythagorean challenge. That is, it's about the very important Pythagorean equation, which is about a right triangle. A squared plus b squared equals c squared. To prepare for this challenge, it may be helpful if you look at my previous Pythagorean math video if you haven't already, particularly the second half of that video. For this challenge, imagine that you have an inexhaustible supply of toothpicks all the same length, and in this challenge you are not going to break any of the toothpicks. You also have a vast flat area on which to lay the toothpicks. The challenge is to create from the toothpicks a square with a right triangle built on each side of the square. 4 different right triangles surrounding the square. It might look something like this. You have this inner square, meaning all 4 sides of it are the same length, and built on each side you have a right triangle. 4 different right triangles, and this is built of the toothpicks, and you can't break any of them, and that simply means that all the lengths involved have to be counting numbers. That is, numbers from the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on indefinitely. And the information I need from you is, what are all those lengths? What are the lengths of each side of each of the 4 right triangles? There are, in fact, infinitely many correct solutions to this challenge. Any one of them will be fine with me, but I encourage you to find the solution that uses the smallest number of toothpicks. Here is my solution. In the solution video to my original Pythagorean challenge, I developed the finding of a number of Pythagorean triples, that is, groups of 3 counting numbers that satisfy the equation a squared plus b squared equals c squared. The first Pythagorean triple in that solution video is by far the best known. It is 3, 4, 5, talking about a right triangle with legs length 3 and 4 and hypotenuse length 5. Well, the study of similar triangles in geometry tells us that we can take the lengths of the 3 sides of a triangle and multiply them by any positive number, and we get new lengths of a new triangle that will be similar to the previous one. That means it will have the same shape as the original triangle. And that means that we can get a whole family of Pythagorean triples from this 3, 4, 5 group of numbers by simply multiplying the 3, the 4, and the 5 by various counting numbers. I have just multiplied the 3, the 4, and the 5 by 2, then by 3, then by 4, then by 5, thus generating the beginnings of a family of Pythagorean triples, a family that has infinitely many members. So each of these is a Pythagorean triple. For example, 6 squared plus 8 squared really does equal 10 squared. 9 squared plus 12 squared really does equal 15 squared, and so on. So these could be the lengths of sides of right triangles. Well, in what you see here, I notice a pair of 12s, also a pair of 15s, and also a pair of 20s. I'm going to go with 12. If I could find two more Pythagorean triples in which one of the numbers is a 12, I would have a solution to this challenge. Well, in that same solution video to the first Pythagorean challenge, the next Pythagorean triple that I developed after 3, 4, 5 was 5, 12, 13. So there's another Pythagorean triple containing 12. I have three of them now: 9, 12, 15, 12, 16, 20, 5, 12, 13. I will look for a fourth one. To try to find a fourth one, I will use the method that I developed in that same solution video. That method is to start with a positive number, square it, divide by 2, and then add and subtract 1/2. Well, I'm going to start with 6. I square 6, that gives me 36. I divide it by 2, that gives me 18. I add and subtract from 18 1/2. That gives me, subtracting 17.5 and adding 18.5. And indeed, we can verify that 6, 17.5, 18.5 satisfy the Pythagorean equation. Now I will double each of those. That is, I'll multiply each by 2. And that gives me 12, 35, 37. So here is a fourth Pythagorean triple containing 12. And again, we can verify it. 12 squared plus 35 squared actually does equal 37 squared. And so here we have 4 Pythagorean triples all containing 12. 12, 35, 37, 9, 12, 15, 12, 16, 20, 5, 12, 13. And so, although this is not drawn to scale, our diagram could look something like this. Here you have the inner square, 12 units on each side, and built on each side of the square you have a right triangle, 4 different right triangles. I said in the original video that there are infinitely many correct solutions. To generate an infinite supply of solutions, we could take these numbers and multiply each by 2, then by 3, then by 4, then by 5, then by 6, and so on indefinitely. To my knowledge, this is the one solution which involves the smallest total number of toothpicks. So that is my solution to my Pythagorean toothpicks challenge. Thank you for watching this solution video.